Okay, so question 2, again, important information here. We've got 70 volts at the start and we've got a motor rated at 2.5 kilowatts. Okay, and it asks you to explain what this means. There's probably two ways you could explain this. So if we look at this, this rating is the max power that this Dodgem can give out. So that's 2,500 watts of power. That's when it's run at a maximum of 70 volts. Okay, so that's what those two things mean together. Or the other way that you could describe this is say that 2,500 joules of electrical energy is converted to other forms every second. And here I guess what it's going to be transformed to mostly will be kinetic energy. Okay, but make sure you don't say things like 2,500 joules of electrical energy is used every second, okay, because it's about it being converted from electrical energy into other stuff. Either one of those would have been fine, either one of those would have got you an achieved. Part B then says calculate the maximum current drawn by this motor. So the equation you were looking for here is P equals IV, because we've got power, we've got voltage, and current is what we're looking for. So if you just rearrange that to get P over V, so you're going to put those values in, it gives you 35.71 or 36 amps, I guess, if you're rounding it to two significant figures. That again was just an achieved question because it's only putting things into an equation. So then it tells us that cars have also got two headlights which run off the same 70 volts as the motor, so we're going to be using the same voltage here. And we've got two lamps here, both with resistance of 4 ohms each. So it says calculate the total current drawn from the supply in this arrangement. Now there are two ways that you could have done this, and either way would have been fine. So the first way you could have done it was looked at the current through the lights. Okay, so just using Ohm's law, V equals I over R. If we just rearrange that slightly, we've got the voltage 70 volts, and because these two things are in series in this branch, then R total for that branch is going to be R1 plus R2. So 4 plus 4, I hope, is 8. And so we get 8 ohms to go in here, and that gives us 8.75 amps. So that's basically the current across this branch of your circuit. So I total then becomes quite easy because we know already from part B that we've got 35.71 amps running through the motor, and now we know we've got 8.75 amps across our lamps, so that gives us 44.46 amps, or 44 amps if we're rounding it to two significant figures. That, believe it or not, is an excellence question, and that would have got you excellence. I think that was relatively straightforward. There was another way that you could have looked at this question, if you find it easier, and I know a couple of people did do it this way. You could have looked at the resistance of the motor. Okay, so that would have been V squared over P. If you look at rearranging Ohm's law and this equation slightly, so then you would have got 70 squared over 2,500, and that would have given you 1.96 ohms. And then if you looked at R total, you would have got 1 over 8 from this branch plus 1 over 1.96, because these two things are in parallel. Sorry, that's 1 over the total. Okay, and if you sort all that out, R total becomes 1.57 ohms. That's equal to R total. once you've got our total for the whole circuit, then obviously I is just V over R total. So that's then 70 divided by 1.57. But that again still gives you, oops, same answer. Okay, so either one of those would have been fine, and both of those would have got you an excellence for that. Over the page, this top one was just a merit question. So it says, one of the light bulbs pops and stops glowing. Explain what effect this has on the voltage across the other bulb. I think this was one thing that you didn't read very carefully. Some of you were talking about the current, the resistance, and a whole load of other stuff, but it just asked you what the voltage would be. So obviously if you've got two bulbs in series like this in any circuit, if this one stops working, there's no way the current is going to flow through the other one. And you know, even if the electrons are coming this way or the electrons coming that way, it still doesn't make any difference. They're not going to get all the way through the circuit. So we've no longer got a complete circuit. So that was the most important thing to write down, that the circuit in this branch is no longer complete. So as soon as you haven't got a complete circuit, you've got no voltage, you've got no current, so the voltage across the other bulb has to be 0. And again, I think when you think about that one, it's a fairly straightforward merit question. I guess part 2 was a little bit more complicated, but again, you had to read this one carefully. They were talking about the current here, that's all they were interested in. It was in the current across the bulb here. So what we really needed to think about here was what was happening once we have broken that. We're only going to have one pathway for our current to go around here. So we've got our motor here. So now this branch is broken, so we've just got power supply here, so supply voltage, and we've got our motor here. Okay, so if you flick back to the previous page, this was your circuit that you had. So now we've just got our 70 volts across here, and we've got our 2.5 kilowatt motor here. Okay. So in this case, because the motor is in parallel with the bulbs, the current through the motor pathway is completely unaffected by anything that happens in the other pathway. So because it's unaffected by what happens in the other pathway, we get no change in the current through the motor. Okay, so that's one way you could have talked about it. The other way, which was probably a little bit easier, I think, to talk about, was that the motor will still draw the same current. Because if you go back to what we did on the previous page, when we were looking at this equation over here, over here when you can't see it, we said that I is equal to P over V. The power that this motor is pulling, the 2,500 watts and the 70 volts itself, have not changed. So this current doesn't change, so that current remains the same. If that current remains the same and its resistance remains the same, because it's still the same motor, if you think about V equals IR, so if we arrange this so that I is equal to V over R, if this hasn't changed and this hasn't changed, then this hasn't changed. Okay, so I must remain constant also. So there's no change in the current. And that was an excellence question.